Hello and welcome. This is Dr. Gates. This week one of the things we're talking about are shapes of data distributions. And I want to make a clarification about one thing mentioned in the Desmos activity. In the activity it says that a unimodal and symmetric distribution is normal. That's not quite correct. That is, although the normal distribution is symmetric and it is unimodal, that does not mean that because the data is symmetric and unimodal, it's normal. A normal distribution has very specific properties in addition to the fact that it is symmetric and unimodal. So there are dozens, hundreds, maybe even thousands of different probability distribution functions, which I'll call PDFs. And the normal distribution, which is also called the Gaussian distribution, it's a very common one. It's used often in statistics, science, engineering, economics, and so forth. But it's not the only PDF which is symmetric and unimodal. There are many other very important ones, such as the logistic distribution, the Laplace distribution, students' T distributions. And that's a whole family of functions. And even that phrase, the bell shape curve, that is the bell shape of the normal distribution, is not limited to the normal distribution. All the above, the logistic, the Laplace, students' T, are bell-shaped distributions, but they are not normal. So what is a normal distribution? It's a very specific function, and what you see here is the formula for it. It looks pretty complicated and kind of intimidating, but it's actually something that we can handle. It's just a composite function built up to, we've already stuttered, the exponential function, e to the something, and the quadratic function, x squared. Don't worry about how complicated it looks or intimidating it is. It really isn't. And right now, the main point we need to know is that for data to be normal, it must fit the above function specifically. Not kind of sort of like it, but exactly that function. So here's the problem. You see data that looks like it fits a bell-shaped curve, but is it normal? Could be. In fact, often it is. But maybe the data could be better modeled by some other unimodal symmetric distribution. Now in this class, we're just going to assume the data is normal. That's the distribution we are talking about. In reality, one shouldn't think that just because the data is bell-shaped, that it's necessarily from a normal distribution. And I'm going to do this with a horse analogy for you. You hear about two kids, brother and sister, down on Chincoteague Island. They have an animal named Misty, and they love to ride it. My question for you is, what is the animal? Most of you are going to guess a horse. In that case, it's right. But the point is that horses aren't the only animals that people ride. Horses are probably the most common animal that's ridden, but there's other things that get ridden. I mean, I got a guy here riding a horse. Yeah, he's on a horse. Richter Hauer, he's playing Etienne Navarre. He's riding a Frisian. That's a breed of horse. Famous guy on a horse. Another famous guy on a famous horse. This is Alexander the Great, and 2,000 years later, we still remember the name of his horse, Bucephalus. Peter O'Toole, he rides a horse when he plays Don Quixote. You can see the horse down there. There's Mr. O'Toole. But Don Quixote's companion, Sancho Panza, does not ride a horse. He rides a donkey. And that's actually an important point here. Donkeys are sort of like horses, but they're not horses. And there are other distributions that are bell-shaped, look kind of like a normal distribution, but are not normal distributions. Just like a donkey is not a horse. Sheena, Queen of the Jungle, she rides a zebra. Zebras are not horses. Peter O'Toole rode a horse in Man of La Mancha, but he rode a camel when he played Lawrence of Arabia. And camels are definitely not horses, although they have a lot of the same capabilities. We use camels much like we use horses. They're beasts of burden, they're used in races, they live in herds. So camels and horses, although they don't look alike, actually are functionally pretty similar. But a camel is not a horse. Tarzan sometimes rides an elephant. Elephants, not horses. He-Man, he rides Cringer. Cringer's a battle cat. Battle cats are not horses. Lyra Balakwa rides Yorick Burnson sometimes. Yorick is an ice bear. Ice bears are definitely not horses. Astrid and Hiccup, they ride dragons. Atreyu from Neverending Story, he rides Atrax, brave noble horse of his, unless, of course, he's riding Falcor, who I don't even know what Falcor is. Was he a dragon? Cocker Spaniel? It made no sense to me. I like the movie except for that. The point is, just like if you're riding some critter, it's probably a horse, but it doesn't have to be. If you have data that is symmetric and unimodal, it's probably from a normal distribution, but it doesn't have to be. And although all normal distributions are symmetric and unimodal, not all symmetric unimodal distributions are normal. Okay, well, I've been saying that, so why don't we go take a look at some probability density functions that are symmetric and unimodal. Well, since we've been talking about the normal distribution, let's start with that. Before we start, there's just two things I want to tell you about what a statistical distribution means mathematically. You can turn any function into a statistical distribution if that function meets two criteria. First, the functional value always has to be greater than or equal to 0. That is, something can have a 0 probability, it can have a positive probability, but there's no such thing as a negative probability. So P of x must always be greater than or equal to 0. And then the one is that the area under the curve, in this case our bell-shaped curve, the total area underneath it has to add up to equal 1. And that's simply saying, if we think of it statistically, that all your possibilities are covered in this case. So for instance, if we're talking about rolling a dice, we've got 6 possibilities. If I add up the possibility of getting a 1 or getting a 2 or getting a 3, 4, 5, 6, it adds up to 1. I mean, if you roll the dice, you're going to get one of those numbers. And this phrase, the area under the curve equals 1, is just a mathematical way of capturing that something has to happen with 100% certainty. Don't know exactly what that event might be, but one of the events will happen. So the area under the curve must equal 1. And this curve here is our common workhorse. Haha, get it? Workhorse. Yeah, statistical distribution, the normal distribution. All right, so here we have a normal distribution, nice fine bell-shaped curve, and a few things to say. So for instance, this bell-shaped curve, if you see here, is symmetric around the origin. It's centered at 0, and the median mode of this particular normal is at 0. One of the parameters is called mu, and basically that's just the left-right translation that we've done before. So basically we can move the curve over. Let's say our average is 2, like it's there, we can move it, we can move the curve over. And so one of the parameters of the normal distribution is the one that simply takes, it's just our left-right translation. Let me go back to the origin. A second thing you can do is how narrow or wide the distribution is. But if you remember, I said the area under this distribution always has to be 1. So if I make the distribution wider, I also have to make it shorter to keep the area under it equal to 1. If I make it tall and skinny, or if I make it tall, it's got to become skinnier so that the total area underneath is equal to 1. And what do I mean by area? Well, that we can see by blue. So basically, how much area does what's in blue take up? And whether or not the sum of all that area equals 1, I can actually add that number there. Let's pull this down. So the area, if we go exactly half of it, ooh, yeah, the area is half. We've covered half the distribution, the area is half. If we do all of it, the area is 1. I can change my sigma, which controls the width of it, and make it shorter and wider. But again, the total area underneath the normal must add up to 1. That is the possibility that a number you pick is between -1,000,000 and 1,000,000. I mean, just the total possibility is 100%, you're going to pick some value. So the total area has to equal 1. So that is the normal distribution for you. Basically, part of the complexity, it's basically e to the minus x squared with two numbers, one called mu in there that lets you move things left and right, and another one called sigma that lets you make it skinnier and fatter. And all the other numbers that show up in the normal distribution, the minus 1 over the square root of 2 pi or whatever it is, are all just kind of scale factors to make sure that the area underneath the curve adds up to 1. So that's the normal distribution. We'll go on in a second and look at a few more. Okay, this is a triangular distribution. It's not too common. In fact, I just kind of invented it for this. Point is, it's symmetric. Symmetric around the origin, as you can see here. And it's unimodal. There's a peak to it. It's definitely not normal, though. It's not very bell-shaped. So if this was not a horse, what could this one be? Maybe a bear, or maybe it's a battle cat. I'm not really sure, but it is not normal. So with our little triangular distribution, again, we want the total area underneath the curve to add up to 1. So this is a function which is, let's make it a little different. Let's see, x values can go from -1 to 1. Height can be 1. The area of that triangle would be 1/2 the base. The base is 2. Height is 1. 2 times 1 is 2. Half of that is 1. Yeah, the total area of this curve will be 1. And we have to play with, notice then that in this case, if I want to make the distribution wider or narrower, again, I got to change the height to make sure that the area of that triangle is always equal to 1. That's what makes it a probability distribution. Like I say, I'm not exactly sure what would be modeled by this probability distribution, but mathematically it meets all the definitions. And likewise, we can shift it left, right if you need to, and scale up and down, sort of like we did with the normal. Okay, another distribution, parabolic distribution. Again, don't know what it would be used for, but it meets the mathematical criteria. It's basically an upside down, downward facing parabola, the part between the x-axis and the curve. Again, the total area is going to have to add up underneath this. It has to add up to 1. And this one, well, it's a little better than triangular. I mean, at least it's kind of roundish. So if this is not a horse, it's not normal. I don't know. Elephant, maybe? And so just like the other distributions we've seen, to be a distribution, the total area under the curve must be able to add up to 1. Must add up to 1, no more, no less. We can, of course, move the curve around as usual. We might not want it centered with its mean at 0. Maybe you need it up there at 1, and in which case you can move around. We could also make it a skinnier parabola or a wider parabola. And in those cases, there's got to be this interplay between the width of it and the height of it, so that the area is always equal to 1. All right, well, those distributions, the triangular and parabolic, were just kind of goofy ones. Don't see those too common in the real world. You definitely see the normal a lot. Two other ones, now we'll get to some more realistic ones that actually show up in the real world. And we're going to talk about them, compare them to the normal distribution. One is called the Laplace distribution. Another one in green is the logistic. And although they're both bell-shaped, neither is normal, i.e. Gaussian distribution. So these two distributions, I mean, they're a lot more alike than normal. So maybe these are the logistics, probably at least a donkey. I mean, it's the one in green. It looks a lot like a normal distribution, but isn't quite the same. Yeah, maybe the Laplace, I don't know. You want to make that the zebra or maybe the camel? Take your choice. All right, so normal distribution to remind you, and remember it's a bell-shaped curve. Some of the things we can do with it are move it left, right, still, and then squeeze it or squash it. The important thing is that the total area under it always equals 1. So as always with all these distributions, if we change the height, you've got to change the width also. That is, if you stretch it upward, you've got to squeeze it left, right. So that's normal. Let's throw on the Laplace in red. This is a much more pointy distribution. And I'll get rid of the normal for now. And like the normal, it can be moved left and right. We've got its mean and mode there at the origin. You can move that over if you need to. And it can also be taller and skinnier or shorter and wider. The important thing is the total area under the function will add up to 1. And by the way, doing that total area under a function adding up to 1, that's something called integration. To figure that out, you'll learn that in calculus in a couple of years if you take it. Alrighty now, well, let's look at the last distribution we're going to look at today, called the logistic. Let me throw it up there for you. And that's the logistic. That looks a bit like the normal. So logistics there in green. Let's throw normal back up there. Normal there in orange. They have very, very similar shapes, don't they? But they're actually not exactly. So for instance, let's get rid of the logistic for a second. I've got my normal curve. Let's focus in on a little bit. This is a normal curve. This is the standard normal, mean of 0. Sigma is set at 1, standard deviation of 1. And the question is this logistic that looks a lot like it. It too can be moved around. It has a scale factor. Now the catch is I can't, although they're very similar, notice I can't exactly line up the logistic with the normal. If you look at your graph, the logistic in green basically is a little skinnier. Oops, didn't mean to shift that around. A little skinnier centrally than the normal, but a little wider tails. They are slightly different. And they actually come about in real world scenarios in slightly different situations. And so this is a good one for us to say, oh yeah, we can be a normal, look a lot like a normal distribution, but not technically be a normal distribution. Logistic and normal are different. They have different purposes. They come up in different contexts, and they are not the same. And no matter how you squeeze or stretch the logistic, you can't quite match the normal curve. They are different functions. Alrighty, well that was our whirlwind tour of symmetric unimodal distributions. We threw out, in addition to the normal, had some interesting ones, triangular, parabolic, more realistic, common ones called the Laplace, logistic. They show up often in the real world, probably not as often as the normal actually does. But there they are. So that was a lot of horse talk. So there's a few, I guess I can't call them take-home lessons these days. So your stay-home lessons are that, 1, the normal distribution is unimodal, it's symmetric, and it's bell-shaped. 2, there are other non-normal or non-Gaussian, if you will, distributions that are also unimodal, symmetric, and even bell-shaped. Often, data that appears to be unimodal, symmetric, and bell-shaped is in fact best described by a normal distribution and not one of the other ones. But it's not always true. Occasionally, and in certain areas, some of those other distributions like logistic or Laplace come into play often. And just because you see a bell-shaped curve doesn't necessarily mean it's normal. Yeah, usually it does. Just like if someone says they rode some animal into town, it's probably a horse and not a battle cat. All right, everyone. Well, thanks for listening. I hope this is clarified and given you a little more details on what it means to be a statistical distribution and what it means to be a normal distribution and what it means to be unimodal, symmetric, and bell-shaped. You have a good day.